All right, AS Chem, this is a video for your Unit 6 Celebration of Learning. I'll be going through a study guide, doing a couple of problems, and hopefully helping you guys know how to do the problems in case you don't, answering questions that you may have. So we're going to start off in 6.1 where we learned about the mole. Now the big slide that I want you guys to focus in on, this is slide number 14 in the Unit 6 slides, which are on Canvas, but this summarized the 6.1 really well. Basically, how to do all of these problems is you're going to take what you have and multiply it by some fact in fraction form. Now, that fact is going to be either the definition of the mole, 1 mole of a substance is equal to 6.022 times 10 to the 23rd particles of that substance, or it's going to be the molar mass. Okay, so one of these two things is going to be multiplied in here in the fact by what we have in order to get what we want. This is the method of dimensional analysis. And if you do it enough times, it makes a lot of sense. But so let's do that then. Let's do that here. But so if you get confused, this literally is the entire lesson. Okay, so how many moles are in 40 grams of H2O? So you're kind of using our template, right? Let's start off with what we have. So we're going to write 40.0 grams. Okay, so that's what we have. What do we want? Well, we want to find moles. Now you can see I'm leaving some space here, right? Because we're going to have to multiply by something to get the moles. What are we going to multiply by? Well, it's either going to be this or this, right? And the way we know is, well, we want to get rid of grams, so we need to have something where, again, I'm saying this fact is in fraction form, okay? So it's going to be multiplying by some fraction with grams on bottom, and we want to get to moles, so moles is going to be on top. Now, do we have a fact which has, grams and moles together? Well, it doesn't say it here, right? But the molar mass is indeed, right, in grams per mole. And so what we want to use here is number 2, we want to use the molar mass. The molar mass specifically, right, because this was grams of H2O. So we're going to take the molar mass of H2O. Now, you guys know how to do that. Hopefully at this point it's very easy, right? All you have to do to get the molar mass of H2O is to add the masses of 2 hydrogens and an oxygen. So 16 plus 1 will get us 18 grams of H2O for every 1 mole of H2O. We do that multiplication, and you can do that in one of 2 ways. How I like to do it is I like to multiply everything on top, so I'm like, okay, that's 40 times 1, and then we have all of that, and you're going to divide it by the bottom. So 40 divided by 18, we only have 18 on the bottom, so that's going to be 2.22. We have 1, 2, 3 sig figs here, so we should have 3 sig figs here. Final answer is 2.22 moles of H2O. So that's how we do that problem, right? And again, we can see the template here, right? Start off with what you have. You multiply by some fact, either the definition of the mole or the molar mass, in order to get what we want. And so that's how you do that problem. Let's take a look at a couple other ones. How many grams are in 3.7 moles of Na2O? Well, using that same template, right? We are going to take what we have, 3.7 moles of Na2O, and to get to grams of Na2O, we need to have something where we have moles of Na2O on bottom and grams of Na2O on top. What is that? Well, this is again just the molar mass, right? But you note that this time we flipped it, right? And so last time we had moles on top and grams on bottom. This time we have grams on top and moles on bottom, and that's simply because that's what will make the units work. Sometimes students say stuff like, oh, I thought the thing that needs to be true is on bottom or something, and and other things, other misconceptions, but no. Hear me say this. It's going to be always what you want to cancel will be on bottom, and what you want to have at the end will be on top, okay? So 1 mole is how many grams? Well, we take a look here, and we're like, okay, Na, there's 2 of them, 23 times 2 is 46, plus O, that's going to be 62. 62 grams of Na2O for every 1 mole. Let me put that into our calculator. Put 3.7 times 62 divided by 1. But anything divided by itself is just 1, or is just itself. Sorry, anything divided by 1 is just itself. We had 2 sig figs here, so at the end we should only have 2 sig figs. That should be 230 grams of Na2O. And there you go. Right, continuing on, how many atoms are in 14 moles of cadmium? Well, 14 moles of CD. To get to atoms, what are we going to need this time? Well, let's see, we're gonna need to multiply by something with atoms of cadmium on top and moles of cadmium on bottom. What we see is that this time it's not gonna be the molar mass because it's not grams and moles, it's gonna be moles and particles. So it's the definition of the mole. Now remember, the particle can be either molecules or atoms, right? And so in this case, it's atoms because it's CD, it's just a single element. So 1 mole is 6.022 times 10 to the 23rd. Moles cancel, and with the calculator, we get 14 times 6.022 times 23rd, you get 8.43. Let's see, we only had 2 sig figs, so we should only have 2 sig figs at the end. 8.4 times 10 to 24 atoms of cadmium. Very nice. All right, continuing on, how many moles are in this many molecules? It's just the opposite, right? 4.3 times 10 to the 22 molecules of H3PO4. How many moles is that? Well, we're gonna want to multiply by molecules on bottom and moles on top. Sorry, just like to be thorough with my units. And so, okay, well, 6.022 times 10 to the 23rd molecules is equal to 1 mole. And so molecules cancel, and we're left with, now do note, whenever you do this, okay, please, I need you to be careful. Numbers in scientific notation, you should put in parentheses. I guess I didn't do it here because I knew it was just multiplication, but basically here we're gonna divide, right? We're gonna see this times 1 divided by this. Really, especially when you start to see divide, you really need to be careful. You need to put those numbers in parentheses. So 4.3 times, 4.3 times 10 to 22nd, okay? Times 1, you don't really have to do times 1. But then we're gonna divide by the bottom, so it's gonna be divided by, again, in parentheses, 6.022 times 10 to the 23rd. So all of that number you're gonna put in parentheses, and you're gonna get 0.07 moles of H3PO4. There you go. All right, so please put your numbers in scientific notation, all of it, the whole thing, in parentheses in your calculator. Cool, okay. So how many molecules are in 48 grams of NaOH? So 48 grams of NaOH. We want to get 2 molecules of NaOH. And so what we think we should do is we say, hey, well, all I gotta do is multiply by something with molecules on top and grams of NaOH on bottom. Right, molecules NaOH, grams of NaOH. Now the problem is, though, you will see, take a look at this. Is there a fact that gives us the number of grams with the number of molecules? Right, is there something that gives us grams and molecules? Well, what you'll see is that the definition of the mole, the first one, tells us the number of particles, molecules in a mole, but it doesn't tell us the number of molecules in a gram of a substance. And our second thing, the molar mass, will tell us the number of grams in a mole, but it's not telling us grams in a molecule, right? So what we see is this actually a little bit trickier, right? We can't just do it in one step. You need to actually multiply by 2 things. What you need is to first go from grams to moles using the molar mass. Right, now you might say, but the question asks us to get the molecules, and I'm like, yeah, that's true. But so then what you can do is, once you've used the molar mass, you can then use the definition of the mole, right? Say, okay, well, yeah, then the moles of NaOH all go to molecules using that fact, right? So basically, grams of NaOH, right, the molar mass, Na is 23 plus 16 plus 1. What is that, 40? 40 grams, roughly, of NaOH is equal to 1 mole of NaOH, right? Then 1 mole of NaOH is equal to 6.022 times 10 to the 23rd molecules. I didn't have enough space, I wrote it up there, right? And then what we see is that grams and grams cancel, moles and moles cancel, and we'll be left with just molecules. And so this actually, this works out really well. Now you might say, how do I put that in my calculator? Well, what you're doing basically is, right, we're just gonna multiply 48 by 1 and by 6.022 times 10 to the 23rd. Right, so that's gonna be our top kind of here. And then we're gonna take that, okay, and I'm gonna put it in parentheses, and then divide it by 40, I'll get something. And then I'll also divide it by 1, but again, that's just going to be the same thing, right? So I'll get 7.2. I have 2 sig figs here, so 7.2 times 10 to the 23 molecules of NaOH, right? And so do note, right, please, you're going from grams to molecules or molecules to grams, right? Be careful, you're gonna have to have 2 steps. Now you could have also done it like 48 times 1 divided by 40 and gotten the number of moles and then did the second step. I like to do it all in one go, but yeah, I am doing 2 separate things, right? I'm multiplying by 2 facts. But yeah, so continuing on, how many grams are in 4.63 times 10 to the 24 molecules, right? Again, this is just kind of similar, it's just the reverse. So 4.63 times 10 to the 24 molecules, CCl4. Right, to do that, to get to grams, I'm going to have to multiply by 2 things. I'm going to have to first multiply by molecules and moles, right? It's going to be 1 mole is 6.022 times 10 to the 23 molecules. And again, remember, I'm going to put these things in parentheses. And then to go from moles to grams, then we can use molar mass. 1 mole is how many grams of CCl4? 35.5 times 4. 35 times 5, 35.5 times 4 plus 12, it should be 154. 154 grams. Cool. Molecules, molecules, moles, moles, and we're left with just grams. Cool. Okay. Putting that into our calculator, we're going to get 0.63 times 10 to the 24 divided by 6.022 times 10 to the 23rd, and we'll get 7.68 times 154. We'll get 11184. The problem is we only have 3 sig figs at the beginning, so I should only have 3 sig figs at the end. 1180 grams of CCl4. So there you go. So that's how you do the mole. Now there's a couple other problems, but they are pretty similar to this. It doesn't get any harder than that. And so, yeah, we're gonna let you kind of do those. But then we go on to 6.2% composition and empirical formula. And yeah, these are 2 different types of problems. They're really kind of opposites of each other. In percent composition, what we're doing is I'm giving you a formula. I'm asking you to go to percent. And then in empirical formula, I'm giving you a percent. I'm asking you to give me the formula. Right? So it's kind of opposite. They're opposite in terms of their how do we do it. But yeah, so let's walk you guys through it. So the first one, how to get percent composition, I kind of wrote out this little explanation for you guys, right? But basically how you get percent composition is just 2 steps. For one, you get the mass of your compound, right? So for example, if we have CH4, you take the mass of CH4, right? That's 16. And then what you do is you take the percentages, right? And so that's always going to be part over whole. And so the percent of C is going to be the mass of C, that part, over the whole, the mass of CH4, all that times 100. And so the mass of C is 12. Over 16.04 is 74.8% approximately. And the percent of H is the mass of H over the mass of CH4, 4.04. Divided by 16.04, so that's going to be 25.2. If you're wondering how I got those numbers, right, it's just from the periodic table, adding them up. So anyways, that's how you do it, just 2 steps. And so let's give you, let's do maybe number 2, because that's a hard one. So what's the percent composition of NH42, SO4, right? To do that, first we're going to have to get the mass of NH4 SO4, and you might be saying that is so complicated, and yeah, it's kind of tedious, but it's not really hard. So okay, we have 2 nitrogens and we have 8 hydrogens. Now you might be saying, how did I get that, right? But basically what we're doing here, if we have NH4 what that means is we have NH4 and then another NH4. Okay, it's saying we have 2 NH4s, right? And so what we can see is 1 2 nitrogens and then 4 plus 4 8 hydrogens. Then we have 1 sulfur and 4 oxygens. And so what we can do is take their masses. So 2 times the mass, oh, sorry, that's an electronegativity chart. Please don't get those confused, right? The electronegativity chart is very different than the periodic table. It gives different numbers. So 2 times 14.01, 8 times 1.01, right? Sulfur 1 times 32.06, and then 4 times 16 for oxygen. Cool. Okay, so it's going to be 28.02. It's going to be 8.08. This is 32.06. This is going to be 64. Put that all into my calculator, and we'll get 132.16 grams, or sorry, actually, I'm still in AMUs. Right, okay, so that's the mass of NH42SO4. And so anytime you see the subscript 2 in parentheses, right, means we have 2 or 2, 3, however many of that thing in the parentheses. Okay, so that's the mass of NH42SO4. So what's the percent of nitrogen, for example, right? So the percent N is going to be the mass of N over the mass of the whole, all of that times 100. And so NH42SO4, that's going to be 28.02 divided by 132.16, all of that times 100. And so we put that on our calculator. So we get 21.2. So the amount, the percentage of nitrogen by mass is going to be 21.2% in this compound. Now, again, for percent comp, it's asking you for all of them, so we have to do it for every single one of them. So I'm just going to kind of make myself a little bit of space here, saying, okay, percent hydrogen is going to be 8.08 over 132.6 times 100. And so that is going to be 0.08 divided by 132.16 times 100. It's going to be 6.11%. And then the percent sulfur is going to be 32.06, 32.16, all that times 100. So 32.06. divided by 132.16 is going to be 24.2%. And then the percent oxygen is going to be 64 divided by 132.16. All that times 100. 64 divided by 132.16 is going to be 48.4. Right, and so this is the percent nitrogen. This is percent hydrogen. This is percent sulfur. This is percent oxygen. And so that's how we do those type of problems, right? All you have to do is get the mass of your whole compound and then just take the percentages of that mass, right? Part over whole. And so that's how we do percent composition. Now, how to do its opposite, percent to formula to determine its empirical formula, that's a little bit more complex. And so I've also kind of written out a little bit of a how-to for you here, right? Basically what we're going to do here is we're going to go from percent to grams to moles to formula. And so to do that, we're going to first assume a sample size, and what I'd recommend is to assume 100 grams, just so you have easy numbers. We discussed in class that it doesn't matter what your sample size is, right? If you have 1 gram of salt, it's going to be NaCl, versus if you have 200 grams of salt, it's still going to be NaCl. And so no matter what, you're going to have the same formula. It doesn't matter what your sample size is, so assume 100 just for easy numbers. Then you're going to go from grams to moles using molar mass, and then you're going to create the simplest whole number ratio of moles to be able to get your formula. And so let's kind of logistically do that with this one. Okay, so we have a compound that has carbon, hydrogen, and oxygen. What we want to do is determine its empirical formula. And so kind of let's do that first step, right? We're going to go from percent to grams. And so we're going to say, okay, 40% carbon, 6.7% hydrogen, and 53.3% oxygen. We're going to assume 100 grams. And so then we're going to get 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Cool. Okay, so that's the first step. And then we're going to go from grams to moles by using the molar mass. And so 40 grams of carbon is going to be equal to how many grams of carbon? Well, it's going to depend on its molar mass. 40 divided by 12 is going to be 3.3 moles of carbon, and then 6.7 grams of hydrogen times 1.01 grams of hydrogen over 1 mole of hydrogen is going to be 6 divided by 1.01 is going to be 6.6 moles of hydrogen. And then here, 53.3 grams of oxygen is going to be 16 grams of oxygen, 1 mole of oxygen. Okay, 53.3 divided by 16 is going to be 3.3 moles of oxygen. Cool. Okay, so then to get whole number ratio, what we're gonna have to do is take these and divide all of them by the smallest of the three. Now, interestingly enough, actually, with this one, apparently these 2 moles became the same. That's not going to be the case normally, right? That's just, this was kind of coincidental. But so of these 3.3, right? These 2 are the smallest. And so what we're going to do is we're going to divide all of them by 3.3, right? So we have 3.3 moles of carbon for every 6.6 moles of hydrogen for every 3.3 moles of oxygen. And so what we do is we divide all of them by 3.3. So what we get there, obviously for these, we're going to get 1 mole of carbon. 6.6 divided by 3.3. I'm not a math guy, but that should be 2. There you go. Right? So 2 moles of hydrogen. And then here it's going to be just 1 mole of oxygen, right? And so this is our ratio. Now, what the heck does a ratio do? Remember, the ratio tells us the formula, right? So really what we had here is we were like, hey, we have carbon, hydrogen, and oxygen, right? But basically, we didn't know, right? We had question marks here. It was like, okay, what should go in these little boxes? And so it's like, okay, well, it's going to be 1 carbon for every 2 hydrogens for every 1 oxygen. Now, of course, we don't really write it like that, right? We just write CH2O. And so there you go. That's going to be the formula. And so you guys recognize this molecule, right? This is CH2O. This is formaldehyde, right? The molecule that looks like this that we saw a lot when we were doing organic chemistry. And so, yeah, there you go. Fun little problem here. Real life. But anyways, so that's how you do empirical formula, okay? Kind of 3 steps: percent to grams, grams to moles, and you get the simplest whole number ratio by dividing by the smallest of the 3, or by dividing the smallest number, by dividing all numbers by the smallest number in the ratio. Cool. Okay, so anyways, let's continue forward. On to 6.3, solutions. So solutions, if you remember, for one, we learned just a ton of vocabulary, and so please do check out my good friend with his solution songs again, right, if you need any reminders, but also hopefully we learned it pretty well. And so this is just a little review of that vocabulary. So a solution, remember, is a mixture that is homogeneous, right? So this is going to be C. And again, if you don't know these are, they're just definitions, right? So it's not anything it's like, okay, why is that? These are just, again, it's definitions. So you're just gonna have to know it, right? So a solution is a homogeneous mixture. A solute, that's the thing that's being dissolved. That's A. The thing that does the dissolving is the solvent, right? So that's gonna be D. And then soluble means that it's capable of being dissolved. And so actually, I'm sorry. Right, and that's nice that we did all of them because I can check my work, right? That's not A. The thing that's being dissolved, that is dissolved, okay, should be B. So CB, D, A. There you go, cool. So that's the vocab. What's the solute and the solvent? Remember, the solute gets dissolved. Generally, that's going to be the thing that's less versus the thing that does the dissolving is going to be the thing that's more. It's going to be the majority generally. Now, if you have water, though, water is always going to be, it's what we call the universal solvent. And so water generally is going to be the solvent in a solution. But so anyways, we got 50 grams of solid NaOH and 150 milliliters of liquid ethanol, right? Also, generally, if we take a solid and put it in water, it's going to be the, if we take a solid and put it in liquid, generally that solid is going to be the thing that's being dissolved. And so here, yeah, the NaOH solid is equal to the solute, and the ethanol liquid is equal to the solvent. Okay, laughing gas, which is 40% nitrous oxide gas and 60% oxygen gas. Well, the majority is the oxygen gas, and so the oxygen gas is equal to the solvent versus the nitrous oxide gas is going to be the solute. That's what's going to get dissolved. And then lastly, steel composition. We have all these things. These are all going to be dissolved inside of the iron because that's the majority. So the iron is the solvent versus the carbon, silicon, phosphorus, and molybdenum are going to be the solute. So there you go. So solute and solvent, some fun and reviewing of vocab. Then calculations, right? The big thing with the calculations, there are two formulas that you need to know here, right? Molarity is equal to moles over liters, and then the dilution equation is M1V1 is equal to M2V2, where this is kind of our before, and this is our after. And so, yeah, so this is kind of like molarity before, this is volume before, it's going to be molarity after, and this is volume after. Cool. So those are the two kind of equations that you need here, and so let's apply that to a couple of calculations. So what is the molarity of a solution with 2.3 moles of sodium chloride? So it's asking for molarity. So it's like, okay, what's molarity? Well, the moles is equal to 2.3 moles of NaCl, and then the liters is equal to 0.45 liters. Cool. So molarity is equal to moles over liters. That's our equation. So therefore, molarity here is just 2.3 moles over 0.45 liters. Put that in our calculator. And you get 5.1 moles over liters, which is what molarity is, right? The other thing you could have written is you could have also said 5.1. Just capital M, right? That's another way of saying molarity. But yeah, okay, so that's how you do that one. This one is kind of similar. Now do note also, I just wanted to point out, you always have to have it in liters, okay? So if we go down to number 3, for example, right? What is the molarity here? It's a similar question. Okay, yeah, the moles is equal to 0.09. It's asking for molarity. We know the moles, and it's telling us that the liters is equal to 12 milliliters, right? And so we're seeing the problem, right? Liters is not milliliters, so you got to convert from liters to milliliters. How the heck do you do that? Remember that it's 1,000 milliliters is equal to 1 liter. And so here, right, all you have to do is say, okay, 12 divided by 1,000 will get us the liters. And you might be saying, does that make sense? And yeah, it does actually make sense, right? You're going to have a very small number here, right? Small, 0.012 is very small, right? Of the big thing, liters, right? Versus, yeah, you're going to have a bigger number, 12, compared to 0.012 of the small thing in the liter. So yeah, actually that does make a lot of sense. Anyways, so make sure you convert, okay? So molarity here, therefore, is going to just be 0.09 moles over 0.012 liters. So it's 7.15 m. So there you go. Going on to number 4, it's asking us for molarity again. But what's happening here is they're giving us grams. They're not even giving us moles. And so to get moles, we have to convert grams to moles. Now it's also not giving us liters, give us milliliters, and so again, take that divided by 1,000, 240 divided by 1,000 will get us 0.24 liters. Now moles is a little bit of a harder ask. 120 grams of calcium nitrite. What the heck is nitrite? Well, remember, calcium is Ca plus 2 in an ionic compound. And why am I saying ionic? Well, because remember, nitrite is one of our polyatomic ions, which we need to know. And so nitrite is NO2 minus 1, right? Nitrate is NO3 minus. Nitrite is NO2 minus. So anyways, we're going to have two of those, so it's going to be CaNO2, right? Because we need two minus ones to kind of balance out the plus 2 of Ca. So we have 120 grams of that. Well, what's 1 mole of that? Well, 1 mole of CaNO2 is going to be equal to how many grams? Let's see. It's going to be NO2 is 14 plus 16 plus 16 times 2 because there's 2 of them, plus 40 for the Ca. So it's 132 grams of CaNO2 is equal to 1 mole of it. And so therefore, when we do this, 20 divided by 132, right? Because 120 times 1 divided by 132 is going to be 0.91 moles of CaNO2. So we put that here, and then we get molarity is equal to moles over liters. Then at that point we can just plug it in. So it's 0.91 over 0.24. It's going to be 0.24. So that's going to be 3.79, although it really should be 3.80 because we only had 2 sig figs at the start. So we should only have 2 sig figs at the end. Oops, sorry. All right, so there you go. That's how you would do that one. Continuing on, at some point we got to dilutions, right? And so as we mentioned, the formula for dilutions is simply this: M1V1 is equal to M2V2. And so let's say number 7, right? We have, so this is kind of like what we have at the beginning, 340 milliliters of 0.5 molarity NaBr. And it's asking, what will the concentration be if I add 560 milliliters? So after, we're going to have an extra 560 milliliters. So what we're saying is, M1, the concentration at the beginning is 0.5, and our volume at the beginning is 0.340 liters, right? That's 340 divided by 1,000 to give us the volume in liters. And then we don't know the concentration after, right? Because that's saying, what will the concentration be? So we don't know that, but we do know that at the end, we're gonna have 340 plus 560. Okay, so please don't get confused. Sometimes kids are just like, oh, the volume at the end is 560, but that's not what it says. It says if you add 560. So 340 plus 560, at the end, we're gonna have 900 milliliters or 0.900 liters. Cool, so then M1V1 is equal to M2V2. Solving for M2, because that's what we're trying to get, we're gonna get something like this, right? Where M1V1 divided by V2 is equal to M2. And so then we can just plug it in, 0.5 molarity over, or times 0.340 liters divided by 0.900 liters. Liters are going to cancel. We'll be left with just molarity at the end. And so M2 is equal to, just to kind of show my train of thought, M2 is going to be equal to 0.5 times, 0.5 times 0.340 divided by 0.900. It's going to be 0.19. I should really say molarity. NaBr. right? So that's going to be the molarity at the end. Now, we can check our answer, right? If we had 0.5 molarity at the beginning and then we diluted it, so we made it less concentrated, then it makes sense that we went down to 0.19. Actually, it does, right? And also, we more than doubled the volume. We went from 340 to more than double, right? If it was double, it would have been like, what, 680? But no, we went up all the way to 900 milliliters. So yeah, we more than doubled it. So it makes sense that our concentration more than halved. So yeah, that actually our answer makes a lot of sense. And so you can do the rest of those in the same way. At the risk of this video becoming too long, I'm just gonna end off with, right, it says here 6.4 will also be in the celebration, but please just do the practice problems. So let me just walk you through a couple of the practice problems for 6.4. For 6.4, right, there was 3 things that we learned. For one, we learned dissolving rules. Will it dissolve in water, why or why not? And remember, what we said is that there's going to be 3 compounds. There's 3 kind of types of compounds. There's more than that, but here's at least 3 of them that we learned. Right? There's ionic compounds, and then there's a covalent, but there's non-polar covalent, right? And there's the covalent that's polar, right? And what we've learned is that ionic is charged. There's charges on ionic compounds. For covalent non-polar compounds, there's no charge, but for covalent polar compounds or polar covalent compounds, there is a charge. It's a semi-charge, it's a kind of charge, but it's a charge nonetheless. And so the types of compounds that are going to dissolve in H2O are going to be the ones that are charged. And so it's going to be things like polar covalent compounds and ionic compounds. And so to answer this question, what you need to do is basically be able to answer like, hey, is my compound ionic, polar covalent, or non-polar covalent? If it's ionic or polar covalent, it's going to dissolve, versus if it's non-polar covalent, it's not going to dissolve. So really, this isn't a new concept. It's just it's asking you to apply your previous knowledge of being able to identify compounds, right, which we learned in Unit 5, to something new. So, for example, NaCl, what type of compound is it? Well, first of all, decide if it's ionic or covalent, right? And so remember, what we do is we're like, okay, well, Na is on this side, so it's a metal. Cl is on this side, so it's a non-metal, so it's going to be metal and non-metal, so we know it's ionic, right? And so will it dissolve in H2O? Well, yeah, it's charged, right? So yes, it is charged. Or sorry, well, I should really say NaCl is ionic and therefore charged. If it's charged, it can interact with H2O, which is also charged, and therefore dissolved. And therefore H2O can dissolve it, I should really say. Because H2O is the one that does the dissolving, it's the solvent. Right, so that's the logic here, right? So basically determines ionic, non-polar covalent, or polar covalent. If we go on to, for example, number 3, right, what we see is we have C and F, both of which are non-metal, so we're like, okay, yeah, that's covalent, right? But is it polar or non-polar? And remember, to determine that, right, what we need to do is we need to draw it out. We have CF4, and so, you know, especially if we draw it out with the right structure, which I really should. And if we draw it out with the correct shape, what we see is that it has, you know, dipoles, right? There's pretty big differences between C and F, right? That's a 1.4 difference, but remember they cancel. And so despite the fact that there are dipoles, there's no net pole, right? So therefore, this is non-polar. So therefore, will it dissolve? No. CF4 is non-polar and therefore not charged. Since it's not charged, H2O cannot interact with it and dissolve it. Therefore, it's not dissolved by H2O. Cool. So there you have it. Will it dissolve? Will it not? That's how you do that. Going on to these problems, what effect will each change have on the rate at which strontium chloride dissolves in H2O? Explain with the diagram in a few sentences, right? Basically, this was from that day where I was showing you guys the rock candy, right? And I was like, how can we get this to dissolve better? And we were drawing some pictures on the board. I think this was last Thursday, right? And basically, we discussed 3 ways that you can increase the rate of dissolving, right? We said that if you crush up the rock candy, that'll help. Another thing is if you heat up the water, that was gonna help. And then lastly, if you stir it a ton, if you agitate it is the scientific term, increase agitation, right? That's going to increase the rate of dissolving, right? And so here, right, heating up H2O, what effect is that going to have, right? And what I really cared about was, could you explain it? And so here, heating up H2O, right, what's going to happen is if we have strontium chloride, so I'm just going to kind of draw it like this. Now, actually, technically, it's going to look like this, where there's more strontiums for every chloride. So it's kind of like an interesting little lattice. Should really draw it something like this. Now some of these strontiums right there also plus and they're next to each other, which isn't great, but it is going to be actually I should draw more chlorines. Anyways, if you don't know what I'm talking about, that's okay. Basically right here, strontium is going to be +2, so we're going to need 2 chlorines because that's only -1. But anyways, but it's hard to actually depict that in a drawing because you get all these weird things where like the negatives are next to each other, which isn't true. But anyways, that's fine. Okay, so what's going to happen here? Well, at first, right, the H2O, they're just going to be kind of going around easily. And actually, I should just kind of draw it like this and kind of just give a key. So here, right, the H2Os are kind of just going to be moving normally at first, just kind of taking things along. But then what happens over time, right? What happens over time is if we heat it up, right, those H2Os are going to be moving more rapidly. And so we're still going to have the same number of them, but they are going to be able to move a lot quicker. And so if they can move quicker, right, what's going to happen, I guess that's where the explanation comes in. So this is kind of my drawing. Basically, if H2O gets heated up, the H2O molecules will move faster. Right, and so that's true. That's something we learned a long time ago. If the H2O molecules move faster, then basically they can do their job of dissolving more quickly, because basically what's happening in dissolving, right, is H2Os are moving and plucking off the SR and Cl cations and anions. So if they're moving faster, of course, they can do their job faster. So if H2O gets heated up, the H2O molecules will move faster. Therefore, they will do their job of plucking off SR +2 and Cl- ions more quickly. Therefore, dissolving strontium chloride faster. Right, so this is a basic idea here. You want to have a drawing, and it's always good to have it before and after, and a little bit of an explanation. Right, and so I just want you guys to be able to draw it out, to be able to explain it. And yeah, Continuing on, kind of last set of questions. Will a precipitate form? If yes, indicate what the precipitate will be and explain why. Basically, remember this was kind of the rule I gave to you guys. If product has charge of +2 and -2 or higher, then basically the water cannot overcome the Coulombic attraction here. It's not going to be able to overcome the lattice energy, and therefore it's not going to be able to keep them apart from each other. They're going to come together, they're going to clump up, they're going to become a solid. And so here what you want to do is you want to take a look at your products, right? So it doesn't even matter about your reactants, but it's like, okay, are either of these +2, -2? Well, the Na, right, if it's in an ionic compound, Na is going to be +1, right? Because it's in group 1, it's going to lose 1. Cl is going to be -1 because it's group 7, or 17, it's going to have 7, and it's going to want to gain 1. So this is +1, -1. So that's not going to precipitate. But then Ca, well, that's +2. And CO3 is -2, right? A carbonate, CO3 -2, we have that memorized, yeah. Right, so this is gonna precipitate, right? CaCO3 will precipitate. Why? Well, Ca is +2 and CO3 is -2. There is strong lattice energy here that water cannot overcome. Therefore, Ca +2 and CO3 2 will come together and create CaCO3 will be a solid in the solution, which is what a precipitate is by definition, right? And so that's how you do that type of problem. And so take a look, you know, what are the charges here, and base your answer off of that. And so I'll post kind of a more detailed key. Actually, I think I already have posted a more detailed key for these in the Unit 6 practice problem key. But anyways, hope that helps. And yeah, let me know if you guys need anything